Okay. Today we will cover the fourth chapter. We will go through the combinational logic gates. And from last chapters, if you remember that chapter 2 and chapter 3, we were discussing the Boolean functions in chapter 2 and how we make it in mathematics. I mean, algebraic, like not algebraic, but Boolean mathematics or Boolean algebra, we can say. Then we went through chapter 3 through the K-maps and how to minimize the gates and use the Karnoff map for two binary levels, for two variables, 3 variables, 4 variables, and also we covered some of like give a concept of 5 variables, how to make their K-map, which it is removed from chapter 5, from edition 5 and 6th edition as well, but it is available. It was available in 3rd edition of Morris Mano book. So then we covered like a topic which called don't care conditions, in which we are not interested in that one, which we are not interested about the output, or we don't care about the output. And then we went through some basic programming of Verilog and how to write our circuit in programming or hardware description. Okay, today we will talk about the combinational logics. In this one, as I told you last time, it's just only logic gates, which depends only on the present combination of inputs. The outputs is present only on the combinations of outputs. Let me show you how. For example, you have here the output. You have inputs, which are available in front of you, M inputs here, and you want from these M inputs to get M outputs. N inputs gives you M outputs. So these we call it a combinational circuit. And just if it is like this, if the N inputs give me the outputs after a delay of time only. So there is no any feedback comes from, if there is any feedback comes from the output and again to the input, then this is called a type of a sequential circuit. So in combinational circuits, just we don't want any type of a feedback. This is clear, right? From last time. So when input changes, output may change after a delay, because we say that the delay from one gate to another gate, it gives you what? It gives you just like, it show you the propagation delay of the transfer of the bit, or the process which has been taken for the bit to be converted or transmitted from the input to the output of the gate. And in the same time, it gives you also beside this one, hold on. It gives you also beside the delay of of your inputs. It gives you like you know, show you the level of the circuits. Is this logic gate circuits, how many levels? It is 1 level, 2 level, 3 level, or how much levels it is. So now normally in combinational circuits, we are doing 2 things. One is analysis. Analysis means that I have this circuit, for example, and I want to analyze it. I want to analyze it means I have to find its function. I have to find its truth table. I have to find its K-map. In the same time, for here, like Boolean function and truth table, and also the K-map, which you can get it easily after that. The second one of the combinational circuit is the design. Design means that I have a desired function, which I want to implement a circuit from it. So there is a certain steps for that. You first of all, you have to check all your your variables. You have to check all your inputs. You have to construct your truth table. Then you have to implement the required circuit which you wanted. Let's see, for example, here that a function may be expressed as a Boolean function or truth table, one of them. But let's see, for example, if we go for the analysis of a circuit. If I want to just analyze this circuit, for example, I have to do a certain steps that to determine the inputs and outputs, to check all the inputs. Then I have to check the inputs, the outputs of each gate and just label it. Then after labeling that gates, I have to take its Boolean functions, find its Boolean functions. Then after finding its Boolean functions, I have to find the final results of the Boolean functions which I have it. First of all, I will take it at the gates. For example, we will see it later on in one example in a very detail. We made it. Then we go through it. At the end of that, we have to construct our table. Okay, for constructing then the table, then we have just to repeat our steps. I mean, for different types of inputs, zeros and ones. Let's see the circuit. For example, I have this circuit is given, and this definitely it will not be labeled in the, in the exam or something like this. You have to label this. So the first output of these three inputs, if I have the circuit, basically it consists of like how many ORing gates here? It's 1, 2, 3, while the others are ANDing gates. So when I have it like this, if I go and just try to collect the F2 here, and I want to collect F1 here, the last Boolean expression, I mean the final one, I might face a lot of difficulties during the analysis of the circuit. So what I have to do, I have first to calculate the output of this and write it like terminal 1 or T1. Then I have to label also this as T2. Then this one, it's easy, just it is like the ORing of these three ANDing functions. So it will give me direct the output. And if I take this output from here and I put it inside the inverter, then it will give me F prime or the opposite results for that. And the output of them with when I add F2 prime with T1, it will give me T3. Again, now when I want to calculate now, if I want to calculate F1, it's very easy that it is T3 into T2. So then I will I will write my inputs instead of T2, and I write the inputs instead of T3, and that's it. So after all this, I have to construct my table. All inputs are available here, A, B, and C. Then I bring F1, which it is this one, F2, which it's here, F2, then when I take it is prime, I just put it is value here. So the prime of F1. And here, if I want to see also what is the outputs of each gate, for example, for T1, the output of it like this here, like a summation. Let me go through it in more detail and in PowerPoint, so it will be more easier for you. Let's say that we have the first gate, which it's T2. The output of this is an ANDing gate, A, B, and C, or A and B and C. Now, the second one, it's OR gate, which it is A plus B plus C. The third one here, this one, it is ORing gate, which it has, which it contains of the three NANDing. So it is sum of the products one. Now, this is the result of F2. Okay. Come if I invert it, just I will bring it to here. I will give it a prime or inversion for all. Then according to the De Morgan laws, I have to convert each ANDing or multiplication to be ORed or to be sum, and each sum, this one sum, it will be converted to a multiplication here. Same thing here, this one, A and C, when I invert it, means I will give it a prime, then I will give it a positive. You got the point? So these what I have seen that people from the last quiz, they are doing some mistakes. I mean, they became confused or something like that. It's very simple. Just when you take the inversion, for example, of this, I tell you take the inversion of this or the complement value of this. What you will do, you will invert it all, you will make the prime on it, then you will change it. Each multiplication, you will change it to plus. And each plus, you will change it to a multiplication. It's basically not a multiplication and plus. It is basically ANDing and ORing gates. So these two functions here, they have AND function. After inversion, they became complements as first. Second, they will become OR gate. Please refer to chapter 2 and go to the postulates and the theorems for that, and then go for the duality and the De Morgan theorems there. Again, for this one, you will find the same thing. AC, you will prime it, and you will change it to a from ANDing to ORing. The same thing. The third one, it's the ORing one here between them. Again, it will be. So first it was here, it was basically, it was a sum of product. Now here it's a product of sum. Okay, you change it because it was here, there is like this product, but between among them are sums. So it was sum of product. Here now it became like product of sum. This sum, this sum, this sum. But what is available between them here and here, it is a product. So it is a product of sum. So now this is the terminal here. When you pass it through this, by the way, which I explained it, it was related again to chapter 2. And also we remade it many times, re-studied it many times in chapter 3. But I just repeat it so that it can be, easy for you in future. I mean, so now here the output at T3, what will be? Just you have to multiply this one, or you have to add this result with this one. Now, when you add, and this with this result, just if you multiply A with A prime will be 0. But A into A prime, it will be there. Then into C prime, it will give you the first one, this one. Again, if you come to B into A prime, it will be here. Then into C prime, it will give you this one. And you have to go through the rest one. C into A prime into B prime. You have to remember two things. You are not going to repeat if you have the same duplicated one. For example, A prime, C prime plus A, B prime, C prime, just you will take one. And if you have A into A prime or B into B prime or C into C prime, just you will consider them as zeros. So you will get your result. So this is the final result for this terminal gate. Now, if you take this result now and OR it with your first one, this one, with T2, which it was here, what you will get? You will get F1. So F1 at the end of the day will be like this result: A, B prime, C prime plus A prime, B C prime plus A prime, B prime, C, and the last one, which is A, B, C, which it is here, A, B, C. Okay, so while F2, it's already here. Okay, now if you see now, if you see now from this, if you see now from here, what you will see, this is the truth table. You have to construct now your truth table according to the your circuit. Already now we found the result. We determined the result of F1 and F2. Is my clear? Is my voice is clear? Hello?
Yes, sir.
Okay.
Yes, sir.
Okay. So now we already designed these two and we have their results. Just imagine that I have, like, for example, I have all zeros at the inputs. What will be the result here? What will be the result here? What will be the result here? And what will be at the end the result of F1 and F2 as well? So if I apply them, you can see that the result of the first one, ANDing gate, all of them are zeros, so it is zeros. Even ORing gate, as all of them are zeros, it will be zeros. All the ANDing are zeros, so the ORing of them are zero. But so from here, just I can see that F2, it is zero. Here, the result of it. I will write it there. So according to the procedure of my designing, that first of all, I have to analyze my circuit. First of all, I have to determine the inputs and outputs. I have to label each output gates as I have done here. Then I have to analyze my circuit by finding the Boolean expressions. Then I have to construct my truth table. 4 steps are there. And then I have to repeat with different input values here to check my results. Okay, to construct my truth table, basically. Now, from this result, F2 is 0. I got it. But if I take a branch I want to implement F1 according to the circuit given. This is circuit given by a designer, and I have to analyze it basically. So what I will do, if I take the inversion for this, it will be 1. So 1, when you AND it with 0, it will give you 0. So 0 ANDing with anything, it will give you the result of 0. So 0 with the coming 0 from here, when you OR it, it will give you again 0. So F1 and F2, it gives you the same result, 0. Let's say that I change the bit. If I give C by a bit of 1, for example, I keep it 0, 0, 1. The inputs here. Again here, 0, 0, 1. Here there is no C, so it keeps as it is, A and B. Here AC, okay, 1. B and C, it is 1. Now, look how the situation will be. This will give me the same result here, 0. This one will give me the result of 1. Why? Umayma? Umayma?
Yes, sir.
Why this will give me 1 here?
Because we are ORing it.
That's
and if there is one.
Okay, yeah, you are right. Okay, so this will be 1. What about this, Ihtisham? Ihtisham. Ihtisham, look, like this, he opened just his WhatsApp and he ran. Hello? Okay, anyhow, now the result here will be a 0. Now, if I convert this 0 by put it in inversion, what will give me? Will give me 1. Now, 1 with 1 from here, I will get my result as it is, as what? As a result of 1, because ANDing of 2 ones, it will give me 1. Now, from here, if I can see the output here of F2, it is 0. So I write it here 0. The output here of F1, as it is 1 from this side, and also 0 from here. So it will be like what? It will be like 1 because I am ORing them. It will give me a 1 result. So now, step by step, I construct my table. I will go through a detailed example of this because an exam, there might be, same questions or not same questions. I mean, in the same time. So you have to construct your truth table. You have to analyze your circuit. I mean, in a very good or in a very clear way. So no problem if it takes time, but you will not do any mistake later on. Now, Ihtisham came back. Okay.
Yes, sir, I'm here.
Be careful, brother. Just be with us. Okay. Now, again here now, if I change the bit B, I change it by 1. I mean, like, constructing the table 0, 0, 0, 0, 0, 1, 0, 1, 0 until I reach 1, 1, 1. So if I change the input here, so 0, 1, 0, 0, 1, 0, here 0 1, because as there is no other third input which it is C, here there is no third input which it is B, no third input which it is A. But from the timetable I have just to put the values which I have it according to the labeled input which I have. So let's see now what will be the output of that. If you can see again here, this will give me 0, this will give me 1 because it is ORing, and this will give me 0 again. It will give me the same result of the step 1. Okay, so at the end of the day, F2 by 0, F1, it will, I will get from it, from the output of it, it is 1. Now, let's talk if I have 2 bits, they are 1. I mean 0, 1, 1. What will be the result now here? Be with me so that I will ask, at any time, just I will catch anyone and I will ask him. Okay, if I have it, again, ANDing 0 with anything, it will give me the result of 0. Here, again, ORing 1 with anything, it will give me the 1 because it is, it is a type of plus or ORing 1. Here it will, I'll get 0. Here I will get 0, but from here I will get 1 from BC, this one, because both bits are 1. So when both of them they are 1, the result here will be 1. When I OR them, I will get 1. Okay, when I get 1, it will be inverted to 0. So the output first here, this one, it represents the output of F2. I will write it here. While when now I invert it, passing through the inversion of that, it will give me 0. 0 with anyone will give me, when I AND it, it will give me 0. So the result of this will be, of F1, it will be 0. Now, let's say just if I make the first one. Hello? Okay. F1, if I make A1 by 1 and the others are 0, I will get the same result, and I will just let me construct my table until I reach 1, 1, 1, for example. I will send you the link of this lecture so that I just try to record it, and I will send it also to you so you can revise it as well. Now, when all of them, they are ones here, I mean, all the inputs are ones. What the result I will get here? I will get 1 here. I will get 1 here, 1. But this one here, it will be representing the F2. So F2 will be represented as 1. But when I pass it through the inversion, it will give me 0. 0 with the 1, which is coming from here, I will get 0. 0 with 1, it will give me again 1. So both bits, both Boolean functions will give me the result of 1, 1. So F1 and F2 is like that. Now, what I have to do after this? After this, I have to build my K-map. Now I have F1, I have F2. So F1, it's available at 1 and 2, right? This is when I make the square map, because as there are 3 ABC, so that I have 8 square maps, right? So this at the beginning, it is 0. Second one, here, it's 1. Third one, this one now, it is second one here. This is first one. This is third bit, but this is second bit. So it will take the value, this value. Again, if I come to this one, it's the fourth bit, and this is the 7th bit. Okay, so if you can see, if you have only this small one, for example, if you have only this one, this K map here, you can build your circuit. It gives you the same results. So you can consider it as a verification of your, when you verify your results, which you get it from the simplification of F2 in the previous one, which we did it, Now here you can see that what is here, like, if you can see here, A, this is A, B prime, C prime. Both of them, they are primed, while A, it's not a prime. Then come to this one, for example, come to like here, A, B, yeah, come to this one. So it is A prime because it's 0, and B, then C prime. Then come to the third one here, the second one here, A prime, B prime, while C is fixed. Then come to the last one here, which represents A, B, and C. Okay? So by this way, you got the same result. If you can see, this is F1 here, which you already got it from this one. Let me show you just from this one. It is the same result when you go through the analysis of the circuit. You got this result. When you finished your implementation and constructed your truth table, you got also by and finish it by K-map. Just you verified your result by using what? The K-map, and you verified your result. What about F2? Now, F2, you have it here, which it is like at 3, and it's like at 5, 6, 7. So they are here. Just what you will write their values. Now, what you will do when you have them, these here, you cannot group them because no one is adjacent for the other, if you can see. So you will keep it as it is. But these bits here, they are adjacent. So this bit, this one is adjacent to this, while this one also it's adjacent to the other bit, this one, and these two ones, they are adjacent to each other. What you will do in this case, just group them. When you group these two bits together, if you remember, what was how I group it? I mean, let me show you. Just it was like this here. For example, here A, right, and here B and C. And just you can see now when you please just mute your mic. Okay, so A, either it is 0 or 1. So it is 0. If it is 0, so here it is A prime in this place, and it's fixed by A prime. Here A, it's 1 and fixed by A. Off your mic, please. Okay. Now, if you have here 0, 0, 0, 1, 0, 0 means that B is 0, C is 0. Here, B is 0, C is 1. Here, B is 1, C is 0. No, here B is 1, C is 1, and here is B is 1 and C is 0. You remember, because just we have to shuffle things. Then 0, 0 here, 0, 1. Then I came to this 1, 0, and I came to this one now here and 1, 1. Oh. When I group them, I will get the same result. I will get these values. Is it clear or not? Hello? 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 Do you hear me?
Yes, sir.
Okay. Who is opening his mic?
Don't know, sir.
Okay. Look now, just let's go and continue our presentations. That was the previous one. It was like the designing procedure. It was the analysis procedure. So now we will move to the second step, which in combinational circuits, which is called the design procedure. Design procedure means that I have a circuit, and this circuit, I want to analyze it. I want to drive its truth table. Basically, and then in designing procedure, I have a function. Sorry, I have a function Oh, Abdullah bin Amir. I just he was okay. I have a function and I want to design it. So I have a procedure for that. If you remember in the previous one, I have a circuit, I want to analyze it. Now look,
Kurang
have
this
I have a
plastic
function.
after fun.
Excuse me. Excuse me. Okay, I will I just, you know, maybe the timing of Zoom will finish like after 2 minutes. After 2 minutes we'll finish. So I will make again new one and I will send you the new link. Okay.
Okay, sir.
Okay. I mean, just you have to inform them. I don't know if the people they hear me or not. We will talk for 2 minutes, then it will cut down and I will come again. We will sign out and come again. Anyhow, I have a circuit now. I have a Boolean function here and I want to implement it as what I will do. I will drive it as truth table first, then I will simplify the expression which I got, then I have to implement my circuit. Let's take an example for that. In this, you know, in designing circuit, basically, okay, I have input, I have input and output, and I want to design the core of this circuit. In the previous one, it was what I have. I have a circuit and just I want to analyze it. Now, if I take, for example, the designing circuit of BCD to XS3 code, okay? So from BCD, basically, it is from 0 to 9, okay? After that, I will apply don't care condition. From 0 to 9 means that BCD, it is like a type of 4 bits, as it is from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9. So what I have to do, now I will sign out and I will give you another link because time is finished. I will just make another one. Okay. For these three from A, B, C, D, because it is BCD, it's above 8, it is above 7, above 8. So I have to use like 4 binary digits for the BCD. So 4 binary digits, we know that it is basically until 16, until 15. But in BCD, up to 9, which we are interested about. If something is out of that, we will try to bring it in the range of BCD. So each one of these, each input of these, they will have like 4 outputs. So they have W, X, Y, Z. So for this one, we will construct a 1 truth table, a 1K map and truth table. So 4 bits from 0 to 9, I will have 4-bit values also. Look, for the first one, for ABCD, I will have like W, this one, which I can construct it here. The first output, what by using XS3. Let me make another Zoom link. I will send you because just, you know, it's make me in trouble when I see just about to leave now. I will make another link and I will send you. I will stop this.